Sup guys, welcome back. So today I want to do a question on networks and specifically flow problems because this was requested by one of my students. So let's have a look. The network diagram shows a flow capacity of traffic in cars per 10 minutes along roads between the suburb S and T. So here's my network and I'm starting at S, going to T, so all these different routes along there. A, determine the capacity of the cut. All right, so what edges does this cut go through? So that one there, that one there, that one there, and that one there. So if you don't know which ones to include and not include, make sure you watch my other video on minimum cuts. But essentially, we're not going to include this cut here, at 40, is because essentially it's going in the wrong direction. So in other words, this cut there is already included in that cut there. So I'm not going to count that. So 185 plus 160 plus 170. Plus 160 plus 170. So that cut there is 515. Okay, B, find the maximum number of cars that can travel from S to T in 10 minutes. Okay, so got two options here. One is you can look for the minimum cut and find what the max flow is. But for this one, I'm actually going to use the method where I basically go along every single route and I subtract away the maximum you can go through at any route. So, for example, let me clear this out. I'm going to start by going from the top. So from SAT, this path here. Sorry, there's a plane above. Okay, so what's the smallest number that goes through SAT? Well, that's going to be 185 cars. So what I do is I write 185 first, and I subtract away that number from there, which leaves 0. 190 minus 185 is 5. Okay, so what I'm also going to do is I'm going to highlight the edge that's 0 as I go along. And now I'm just going to repeat the process. Okay, so another path I can go from S to T is just straight through here. So that is SBT. Now the smallest number there is 100. So I'm going to write 100. And I'm going to subtract away 100 from the root. So that's 60. And that's 0. Once again, I'll highlight the 0 edge because that's going to tell me which ones I can't use. Okay, so next is I can go through, let's say, this path here. SCDT. Now the smallest number there is 80. So what I'm going to do is subtract, or write down 80 first, and subtract 80 from all these. So it leaves 30, 0, and 90. All right, highlight the 0, so I can't use that anymore. All right, what other path can I go? So I can, looks like I can do this. Okay, so SBDT, so what's the smallest number there? Looks like it's 40. So I write down 40. I subtract that away, so it leaves 20. 40 minus 40 is 0. 90 minus 40 is 50. And now I highlight the one that's 0 again. Okay, so what do I have left? It looks like I've got just this one edge. Now the smallest number there is 5, so I'm going to write down 5. And I'm going to subtract away 5 from what's left over. So 20 minus 5 is 15. 50 minus 5 is 45, and 5 minus 5 is 0. So, summing all those together should give me my max flow. 185 plus 100 plus 80 plus 40 plus 5. Well, that's 6. I don't know what happened there. So, 410 should be my answer here. Okay, so that's the max flow. All right, so the council plans to increase the traffic flow between S and T. There are enough funds to widen only one road. Which road should be widened to achieve the largest increase in traffic flow, and by how much will it increase between S to T? Okay, now, what's helpful is I've highlighted all the ones that are 0. So what I've got here is I can see which edges I might widen to increase the traffic flow to, I guess, maximize this this network. So what you can see here is, at the moment, right, I've got 30 cars which are stuck there, and I'm trying to get this through the system. So I can see this 30 here is stuck. Now, it's stuck because this one has a capacity of 0 at the moment. But what do you notice here, from D to T, you also have 50 cars that or sorry, you can have space for 50 cars and can fit through. So what I could do is I could increase CD by 30 because that would let, in essence, 30 cars get from C to D. And then once they're at D, well, they can already get through from D to T because the road is wide enough for that to happen. So that answer there will be CD by 30. All right, done. So here's a similar question, and we're going to attack this slightly differently, but let's have a look. So a museum is planning an exhibition using 5 rooms. The museum manager draws a network to help plan the exhibition. The vertices A, B, C, D, and E represent 5 rooms. The numbers on the edges represent the maximum number of people per hour who can pass through the security checkpoints. Okay, so there's your network diagram, once again with a cut. What is the capacity of the cut shown? So once again, I'm going just to look at what's on the path, so 70, 90, 40, and 130. Which ones am I not going to include? I'm not going to include this 41 there because one, it's in the wrong direction, or if you remember from our other video, you can think of the car analogy where basically the arrow takes out the driver, so we're not going to count. Okay, so it's going to be 70 plus 90 plus 130. So that is 290 there. Easy. All right, next one. So the museum manager is planning for a maximum of 240 visitors to pass through the exhibition each hour. By using the minimum cut maximum flow theorem, the manager determines that the plan does not provide sufficient flow capacity. Draw the minimum cut onto the network below and recommend a change that the manager could make to one or more of the security checkpoints to increase the flow capacity to 240 visitors per hour. Okay, so there's a bit there. What they're telling us is they want the max flow to be 240, but currently it's not. And we need to prove that by drawing the minimum cut. So let's have a look. Now that obviously is not going to be there, it's 240. We're looking for a number smaller than 240. Okay, so we did this one before, so it's not going to be that one. Now, what about this one here? Okay, so along this one here, it would be 80, 40, 65, and 45. So let's test that out. So let me just draw that in so you can see. 80 plus 40 plus 65 plus 45. Okay, that's 230. So that actually works. So we've actually got a cut which is less than 240. Well, I'm pretty sure that's going to have to be it. So the min cut is 230 because it's less than 240. Okay, now what that's telling us is we want to improve, or we want to maximize the network by getting it to 240. So the difference between 240 and 230 is 10. So we need to find somewhere or find an edge to increase it by 10. All right, so let's examine this for a second. So you have 240 going into A. Now how much is coming out of A? So coming out of A is 80 plus 90 plus 70. So that's the outflow. Okay, so 240 comes out of there. So we're good so far. We're trying to look for the blockage. So let's have a look here. 80 goes through to B and 40 goes through to B. That makes 120. And 130 comes out. Okay, so that might be a hint there because there's a discrepancy. That's 120, that's 130. Okay, let's look at this one. What goes into C? Okay, so 90 and 25 make what? So 90 plus 25 is 115. Well, what's coming out of C? So that's 40 plus 65. So 105. So do you see that there? So we've got 115 going in and 105 coming out. That means the 10 is in there somewhere. So if we have 115 going through C and 105 coming out, that means we can increase an edge like 40 because it's going to flow on to B and it's going to come out here. So we can actually increase CB by 10 to turn it to 50. And that will be the way to maximize the flow. All right, so I hope that helped. If there's any things you want to see, let me know down in the comments below. But otherwise, I'll see you in the next one.